Now I want to consider the topic latent heat in physics. The word latent from the English word means hidden, but there's actually a change going on. Just that in this context, we have latent heat as when heat is being supplied and there's a change in form without a change in temperature. So when a substance, for instance, that is in its solid state is steadily heated, it eventually changes into the liquid state without a change in temperature. Now this heat that causes this change from the solid to liquid is called the latent heat of fusion. Now there is a change from the solid state to the liquid state due to the heat which is being added, but there is no corresponding change in the temperature. So for instance, if you have your ice block which is at 0 degrees Celsius and you apply some heat into it, there will be a change from the solid ice into the liquid water, and the heat that is required to carry out this is called the latent heat of fusion. There's also the reverse of it, which is when you have to convert it from 0 degrees Celsius of water, that is very cold water, and you have to ice it. There's an amount of heat that is being removed. Now heat is being removed, but there is no change in the temperature. The heat that is being removed will change the state from liquid water into iced water, but there won't be a corresponding change in the temperature. Now on the other hand, when a substance which is in its liquid state is steadily heated, it eventually changes into vapor as it boils without a change in temperature. Now this heat that causes the change from the liquid state to the vapor state is called the latent heat of vaporization, meaning that when you apply heat to water at 100 degrees Celsius, you proceed and continue to increase to add some heat, there will be a change in states and you begin to see vapor coming from that liquid, for instance water. Now there is a change in states, but the temperature of the steam is at first at 100 degrees Celsius. So the heat that caused this change is called the heat of vaporization, and we could have the reverse of it, such that when you have vapor or steam at 100 degrees Celsius, at 100 degrees Celsius, and then you remove some of the heat, there will be a change in states from the vapor state of the water into the liquid state of the water, but still at the same 100 degrees Celsius. These latent heats are dependent on just one thing, which is the mass of the body which is being heated. So we can define specific latent heat of fusion as the quantity of heat which is required to convert its unit mass from solid to liquid without change of temperature, while specific latent heat of vaporization of a substance is the quantity of heat required to change unit mass of that substance from liquid to vapor without change of temperature. And with this, quantity of heat which is supplied is equal to the mass times the latent heat, be it of vaporization or fusion. The unit of specific latent heat is joules per kilogram. Let's consider some examples. How much heat energy is required to change 5 kilograms of ice to water at 0 degrees Celsius? Now perhaps from this you will understand better. The mass of the ice is 5 kilograms. Now it's melted into cold water, and for it to have melted, it means that it must have absorbed some heat from the surrounding, and it would melt into water. The temperature of the ice here is 0 degrees Celsius, and the temperature of the water here is also 0 degrees Celsius. Now we have to calculate the quantity of heat which is required to change it from that state to other, and we have it as Q equal to mass times specific latent heat of fusion. Now, specific latent heat of fusion of ice equal to 336 joules per kilogram. And so we have our mass, which is 5, multiplied by 336 joules per kilogram. And so we have 1680 joules of heat. This is the heat energy that is required to change it from ice into water. Okay, this next question says that what is meant by the following statements? A. The specific latent heat of fusion of ice is 3.36 times 10 raised to the power 5 joules per kilogram. And B. The specific latent heat of vaporization of water is 2.26 times 10 raised to the power 6 joules per kilogram. Now, what does this statement mean? They are saying that specific latent heat of fusion of ice is 3.36 times 10 raised to the power 5 joules per kilogram. It means that 3.36 times 10 raised to the power 5 joules of energy is needed to convert 1 kilogram of that ice into water without a change in temperature. So take note, no temperature change. Having that specific latent heat of vaporization of water to be 2.26 times 10 raised to the power 6 joules per kilogram. It means that 2.26 times 10 raised to the power 6 joules of heat is needed to convert the water into vapor without a temperature change. Now here comes this question. 10 grams of ice at minus 10 degrees Celsius is mixed with 120 grams of water at 80 degrees Celsius. Find the final temperature of the mixture. Taking the specific heat capacity of ice to be equal to 2200 joules per kilogram per Kelvin. Specific latent heat of ice is 3.36 times 10 raised to the power 5 joules per kilogram, and specific heat capacity of water is 4200 joules per kilogram per Kelvin. Now in this question we need to understand it very well. We are told that there's ice, 10 grams of it, and the ice is at minus 10 degrees Celsius, so it has really been freezed such that it has become negative 10. It was mixed with water, hot water, which is at 80 degrees Celsius. Now with this mixture, after some time, we expect to have a common temperature, that is after some time. Now meaning that the ice which is at minus 10 degrees Celsius will not remain at that minus 10 degrees Celsius. Looking at the mass, it has a small mass, and so it is going to be brought, the temperature is going to increase from minus 10, to the positive, and then the water which is 80 degrees Celsius will also reduce. So heat is being gained by the ice, in one word, and then heat is being supplied by the hot water. First, let's get it straight that the mass of our ice is 10 grams, and so we'll convert it into kilogram, and that gives us 0.01 kilogram. And the mass of our water, which is 120 grams, will be changed into kilogram, which is 0.12 kilogram. Now, for the heat gained, there are 3 stages of heat gain. So we want to analyze the heat gained. Now the first thing is that the ice increased. So it increased from minus 10 to 0 degrees Celsius of ice. So here it is still in the ice stage, and this increase is as a result of the hot water that increased it. Then the second stage is that there is a change in state from 0 degrees Celsius of ice to 0 degrees Celsius of water. That is the second stage of heat gain. Then the third stage of heat gain is an increase from 0 degrees Celsius of water to a final temperature, which we do not know yet, and that is what we are looking for. Alright, so let us take this first part. Increase from -10 to this. So we have it as heat gained here equals to mass mc change in temperature, that is mass of ice, specific heat capacity, because you are considering the heat capacity in this place, then times change in temperature. So our mass is 0.01 kilogram times specific heat capacity of ice, which we were given in the question to be 2200, times the change in the temperature, changing from -10 to 0, that is 10. You know, it's just like you have 0 minus 10. This is the final to, then this is initial to the final. So 0 minus -10, we have 0 plus 10, and that is still 10. So that is how we have our 10 in this place. Now when you multiply these two, you would have 220 joules of heat. Then change in state, which is the second stage. In change in state, we'll be looking at ml, as which is equal to the quantity of heat that was gained there. Now the mass of the ice is still 0.01 multiplied by the latent heat of fusion of ice, and in the question we're told it is 3.36 times 10 raised per 5. So 3.36 times 10 raised per 5, and when we multiply all this, we will have 3,360 joules of heat. Now for the third stage, we have increase from 0 degrees Celsius to T2, which we do not know. So this heat gained here is mc change in the temperature. Now this is now mass of this ice which turned into water, not this water, this ice which has now turned into water. So the mass over here now is still 0.01 times the specific heat capacity of water, which is 4,200 multiplied by the temperature change. Now the initial temperature was 0 and the change to a final temperature was T2. So we have it as T2 minus 0. And so we'll have, when we multiply all this, we'll have 42. That's 0.01 times 4,200. That's 42. To bracket T2 minus 0. So this makes nothing. So we have 42T. So let's remember all that these are the heats that were gained by the ice. We have this as well in joules. Now what about the heat supplied? Heat was supplied by the hot water. So the quantity of heat supplied by the hot water is also mc change in temperature, where we'll consider the mass of water. Now the mass of water here is 0.12 multiplied by the specific heat capacity of water, which is 4,200, times the change in the temperature. Now the initial temperature of this hot water was 80, and it's reduced due to the ice. So we'll have it as 80 minus T. That is the reduction. And so when we multiply this, we would have 504 into bracket 80 minus T. And so this is equal to 40,320 minus 504 T. Now taking note that heat supplied equal to heat gained. So we are going to equate all of this. So do not let us forget this. This is the heat that was supplied. So we'll have 40,320 minus 540 equal to heat gain, which is 220 plus 3360 plus 42T. Now when we collect the like terms, we will have 40320 minus 220 minus 3360 equal to 5040 plus 42T. So we brought this minus 504T over to this side. So we have this as T. So when we solve all this, we will find out that all this gives us 36,740. That is this side, and then we add this and this, we'll have 546T. So when we make T the Sawyer formula and we divide both sides by 546T, we'll be left with T equal to 67.29 degrees Celsius. So 67.29 degrees Celsius is going to be the final temperature of the mixture at the end of this experiment. Alright, so let's take this next question. It says 100 grams of steam at 100 degrees Celsius condenses to water at the same temperature. How much heat energy is liberated by this process? So in this question, we're told that 100 grams of steam. So the mass of the steam is 100 grams, which is the same thing as 0.1 kilogram. It condenses into water at the same temperature. That means no temperature change, but there's a change in states. Now we're given that the specific latent heat of vaporization is 2.26 times 10 raised by 6 joules per kilogram. So the quantity of heat that was liberated by this process is mass times the latent heat of vaporization. Here mass is 0.1 and then 2.26 times 10 raised by 6. And so when we multiply this through, we have 2.26 times 10 raised by 5 joules of heat. Alright, so in this next question, we're told that the quantity of heat energy required to melt completely 1 kilogram of ice at minus 30 degrees Celsius is dash. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Specific latent heat of fusion of ice is 3.36 times 10 raised by 5 joules per kilogram. Now here we have ice that has a mass 1 kilogram and the temperature of the ice was 30 degrees Celsius. So we are looking for the quantity of heat that will melt it completely. That means we are going to increase the temperature from minus 30 of ice into 0 degrees Celsius of ice, and then we will now melt it from 0 degrees Celsius of ice into 0 degrees Celsius of water. So the total heat that will be supplied will be used for the entire process, that is MC change in temperature plus ML. What does this mean? This is the heat that will change it from minus 30 to 0 degrees Celsius of ice, and then from 0 degrees Celsius of ice to 0 degrees Celsius of water where it will melt. We have M, which is common on the two sides, so we can factorize by bringing this M out, and we have specific heat capacity times the change in the temperature plus L. So our mass is 1 from the question. The specific heat capacity of ice is 2,200 joules times the change in the temperature, that is from 0 to 30. So the temperature change is 30. So we multiply this plus specific latent heat of fusion of the ice, which in the question was given as 3.36 times 10 raised by 5. Alright, so we have 1 into brackets, this times this, which is 66,000 plus this. This is same thing as 336,000. So when we add this together, we will have 402,000 multiplied by 1. It will still be the same thing. So this is the quantity of heat that will melt this ice from minus 30 degrees Celsius. So in this next question, we're told that a heating coil rated 1000 watts is used to boil off completely 2 kilograms of boiling water. The time required to boil off the water is dash. Specific latent heat of vaporization of water is 2.3 times 10 raised per 6 joules per kilogram. We're told that a coil which is rated, that is the power is 1000 watts, is used to boil off completely a mass of water. So the mass of the water is 2 kilograms. We are given the specific latent heat of vaporization which is required to boil it off, meaning that there is a change from 100 degrees Celsius of the water into vapor at 100 degrees Celsius. So that is 2.3 times 10 raised per 6 joules per kilogram. Now we are looking for the time that is required to carry out this. So we have it that the heat that was supplied by coil equal to the heat that was gained for vaporization. So heat supplied is power times time, which is equal to mass times L. That is mass of the water times the latent heat of vaporization. So we have 1000 multiplied by T equal to mass, which is 2 multiplied by 2.3 times 10 raised per 6. So we make T the subject and we have 2 times 2.3 times 10 raised per 6 divided by 1000. So we have 4.6 times 10 raised per 6. Now this is the same thing as saying 10 raised per 3. And so when this comes up, it becomes 4.6 times 10 raised per 6 minus 3. You could check our class on indices mathematics to understand this further. So we have 4.6 times 10 raised per 3 seconds. So this is the time. 4.6 times 10 raised per 3 seconds is the time that is required to boil off this mass of water.